So here's an outline of my presentation. I'll give a high-level overview of the product, then I will bring up a few topics from Task Group 219, step quickly through some algorithm history leading to why Monte Carlo, go through some quick algorithm basic workflow, give a brief demo. So IMSure 3D software. Well, it's a Monte Carlo-based independent check. There's a patient work list that allows you to review plan metrics, the DVH analysis. There's a dose and gamma slice viewer, review of gamma pass rate. There's a beam data table, plan complexity metrics, and templates for plan evaluation metrics, as well as customizable setup and email notifications. So that you can see how IMSure 3 software fits into your clinic, I've put together a quick diagram. You can think of everything beginning with the treatment planning computer. From the treatment planning computer, once the plan is approved, one exports the RT plan, structures, dose, and CT images. IMSure monitors this export location, and upon finding new plans, automatically imports, launches a calculation, and generates the results and can be set up to send out an email so that when you get notification that you have some plans or you can to review, or alternatively you can just check in from time to time, maybe with your morning cup of coffee every day, and review the plan QA from any computer on your hospital network. So IMSure is a web-based application so that it does not have to be installed on multiple computers. As well, of course, you can export your RT dose and reports to a particular folder location. I wanted to bring up AAPM Task Group 219 and just highlight a few items in a particular excerpt that I have pulled out of the document, particularly at the bottom of page 5, top of page 6, as I downloaded it from the AAPM website. So, of course, everyone's familiar that you should perform IMRT VMAT patient-specific QA. And then perhaps one has been using a 1D, which is still fine, but preferably a 2D or 3D algorithm. And there are some advantages to an independent dose calculation method because it's less time-consuming than setting up a phantom. Such calculations don't require machine time or all of the efforts associated with measurement techniques. And then another statement that I thought was pretty interesting is that these advantages cannot be neglected when evaluating the overall IMRT QA strategy in a department, as personnel feel increasingly confident about the reliability of techniques such as IMRT. It's reasonable to revise efforts in order to reduce the overall workload. And so the more accurate your independent dose calculation is, the more confidence one can feel in leaning more heavily on a calculation method for your QA. The other item that follows shortly after this excerpt is a statement that IROC has observed the surprising result that an independent recalculation dramatically outperformed institutional measurement-based QA in predicting whether a plan would pass the IROC phantom. I've also provided the complete reference if you'd like to take a look at that. But this is some pretty interesting evidence that independent recalculation is quite beneficial in the clinic. So what are the goals of good QA in radiotherapy? Well, we want the QA to be highly sensitive, so there's a low probability of missing relevant errors. We want it to be a decision-based on relevant criteria, things such as the target volumes and OAR metrics, and the delivered dose to the patient from the treatment, rather than the delivered dose to something like uh, uh, a detector array. We want to concentrate on systematic errors, and then as well, a method with high specificity that do not cause excessive false alarms. So dose calculations in general fall into two categories: the more traditional analytical algorithms, uh, and then as well stochastic algorithms. And the only one currently in use in treatment planning systems is the Monte Carlo. So why a stochastic algorithm? And what does that imply? So uh, it implies that each particle uh, is a simulation of a particular an accurate physics process. And so the dose distribution emerges from the superposition of many of these particle tracks and the dose deposition that occurs within the patient anatomy. And so the more particles, the more smooth the dose is. So what you're seeing here are, some particles uh, and the position of their dose deposition. As more particles are added, you can see more clearly and smoothly the dose deposition until you get to a reasonable number of particles. And so the more particles, the smoother the dose. But traditionally, that also was a very long calculation time. Not so now, and I'll go into that a bit more. So why is the Monte Carlo best? Well, because it starts from first principles. Uh, and it's infinitely flexible because it's modular, and each particle fate is independent from all the others. And you follow that independent particle and, use your, roll your dice, for example, or use your uh, random number generator in order to determine, what type of particle is going to be emitted, and how it's going to track then through the patient. Is that photon, for example, going to interact with the Compton scatter, and what are those angles going to be as and where is that dose going to deposit as it tracks through the anatomy? What is shown here is, your aperture, the of course your Monte Carlo uh, uh, dose deposition of what occurs through these leaves and of course in the opening. Things to notice are the gaps in between the MLC leaves, and which you can see here as well. Uh, of course, your backup jaws, and you can of course see the difference in transmission. And so it's flexible because the Monte Carlo will naturally be able to track and use this transmission through the geometry of the particular linac. So let's get back to talking about speed a bit. And how fast can Monte Carlo get before it breaks? So to step back, one would, of course, benchmark to the general purpose Monte Carlo codes, things such as EGS or NRC, EGS NRC or MCNP. Um, uh, EGS NRC is what the Stochastic algorithm has been benchmarked to. And of course, in these general purpose codes, you can model whatever you'd like to, everything from fusion reactors to ion chambers, uh, linear accelerator heads. They're versatile. They contain all materials, all geometries, all types of particles. And they are top-notch algorithms. So how can we get to a really fast solution for a QA system for a patient? So do we really need to be able to model everything? No. And so you can use some uh, some different methods in order to optimize for the patient-specific anatomy and the material composition of the human body. And so in particular, not having to load cross sections for all materials. And then, of course, doing some optimization for a patient anatomy. But at the same time, we don't want to drop this accuracy. And so this is a standard benchmark case that you've probably seen if you've been to many Monte Carlo talks. It's a 10 by 10 beam, 6 MeV monoenergetic particle, traversing through this 150 millimeter ICRU lung slab, and you can see, how the dose changes with depth through this lung slab, and then, of course, the interaction when it goes back into the water equivalent material. And the red dots are the EGS NRC, the blue line is SIMOCA, and you can see there's excellent agreement throughout, particularly focusing on these interface areas. And the key item that I wanted to bring up is that the SIMOCA dose engine calculation is 120 times faster than EGS NRC for this particular benchmark case. So why Monte Carlo? We've shown that it's fast. Everybody knows Monte Carlo is accurate, and shown some examples there. Another thing is, so what is most important? Of course, tissue heterogeneities are important, but the beam model is also very important because there are certain things that need to be correct to reach a 0.5% accuracy level for clinical plans. Things such as the air gap between MLC leaves, those have a very tight tolerance, MLC leaf calibration, the primary photon spectra, radius of primary source, etc. All of these have to be modeled quite accurately. And where does this model come from, and how can we make it generic enough that it's easy to commission and generate models for all of the linacs that are out there that have, of course, slightly different mechanical tolerances. So first one designs a virtual source model. And that, of course, is already done and integrated into the system. And so this is, just to give you a real high level overview. So, you have to know the LINAC design, generate a beam NRC model. And from that beam NRC model, you have to do some analysis of, of the phase space, and then define virtual sources. In this particular case, dependent on the LINAC type, if it's a CyberKnife, if it's Electa LINAC variant, you know, RadExact, whichever LINAC, uh, define the virtual sources required for that LINAC, and you fix most of those source parameters. But then some of the parameters are left open for fitting. Things such as the primary spectra, uh, the focus diameter, manufacturing tolerances, such as your dynamic leaf gap, and that's how you come up with the specific beam model. But to go into this, there are, of course, your typical water tank scans that you have acquired to commission your treatment planning system. So again, why Monte Carlo for patient-specific QA? So one of the issues is that TPS commissioning is problematic, and this has been uh, uh, brought forward by IROC, in multiple publications over the years. The one publication that I already highlighted in Task Group 219 is that the independent recalculation outperforms traditional measurement-based IMRT QA methods in detecting unacceptable plans. So that's an interesting article. And of course, we know that these IROC phantoms, when those are sent to clinics, the pass rates are not as high as we would like to see for our patient treatments. And one of the big things is the beam modeling. Uh, and a real recent article that just came out in 2022 are these beam modeling verifications that predict errors in IMRT dosimetry audits. And this is really telling, and it provides some specific examples of if the model is outside the typical range. It's uh, indicative of a bad model. And so the beam model is very important, and there have been numerous other publications in this area. So the objective with the Monte Carlo second check is to, just throughout the community, try to decrease these 5% variations that are seen and are out there based on the IROC phantom studies, differences even greater than 5%. And so you might ask, well, if you're using this same water tank data to generate your beam model, how is Monte Carlo going to help? And so I'm going to try to explain to you some of the self-consistency of Monte Carlo. So what we're looking at here is a calculated versus a measured PDD for a 4x4 and a 7x7 field. And what you'll see is that uh, the small aqua line is the Monte Carlo electron contribution. The dashed line down here is the Monte Carlo generated secondary spectra. This other dashed line is a Monte Carlo generated primary spectra, all which combine to generate the Monte Carlo calculated PDD. It's in blue, and here there's very close agreement. The red is the measured. And you can see if you look at this green line, that shows the difference, and you have very good agreement for both of these field sizes. But then if one looks here at the 40 by 40 field, the agreement isn't as good. You have some under prediction here at the top, over prediction here at the bottom. So what's going on here? Is this a measurement error? Or have we selected the wrong spectra, for example? And then you can see here clearly in the 10 by 10 field, there is not good agreement. Trying an alternative spectra, you see really good results here for the 40 by 40 field. And then some differences for the 7 by 7 and the 10 by 10. So one, optimizes on the spectra until good agreement is seen across the range of field sizes. And a similar method is used for each of the fitting parameters, such as the source size, etc. And so, of course, everyone works really hard setting their water tanks up, trying to take the most accurate measurements possible. But the truth is, and that this product has a lot of history, and so I'm going to go through and show some interesting statistics on the experience of 140 customers and the beam data that was analyzed, and show that the majority had errors greater than 1 to 3%, and in the worst cases, greater than 9%. And many of these measurement errors translate 1-to-1 into a dose calculation error. And in the previous slide, I tried to explain to you, and hope I've done so successfully, how we know that there are errors. Just real quickly, the different errors, dose errors greater than 5%, items that might cause that, water tank setup issues, defective measurement devices, poor placement of electrometer, operator errors, type 2, not as large of differences, might have problems with beam steering, wrong detector choice, poor positioning of cables and connectors. Type 3, lower errors, perhaps there was some water evaporation over time, not enough water so that your backscatter isn't good at those deeper scans. Not ideal detector. But the real interesting thing that I wanted to show is that 14% of these cases had type 1 errors. So, really not good results from their water tank measurements that were, of course, then used to commission the treatment planning system. Type 2 errors, 26% of the 140. Type 3 errors, 34%. And of course, the others had really nice data. So there is that validation of the base data, the water tank data. So then, just to recap, what are the benefits of Monte Carlo? So, of course, we want the QA of the planning process, using your independent secondary check, the QA of the dose measurements, which I've spent quite a bit of time talking about in order to eliminate errors. And then, of course, there's the QA of the treatment planning system. And so, this can be different items such as your DLG, just confirmation if you have a different system, how the comparison looks. And finally, I'm going to try to tie up, the workflow that is occurring inside of the IMSure 3D calculation system. So there's a virtual source model, which you can think of as the particle generator. Here, from that beam modeling that I've been talking about, random numbers are used to determine the particle type, location, energy, and direction. For example, one can roll your dice or use your random number generator to determine if a photon's going to be emitted or an electron. So what's the probability? About 97% of the time it's going to be a photon. And then next you step on down and see, is it going to be a primary or a secondary photon? Again, you roll your dice or use your random number generator to determine what type of photon, and then, working on down through the system. And so, that's your virtual source model particle generator. The next component is, the plan specific leaf and jaw positions, and those determine the transmission of these particles that are generated, and which actually make it down to the patient anatomy in the form of the CT to go through the real Monte Carlo tracking. Of course, where that photon, you did you roll your dice or use your random number generator to determine, what type of interaction it's going to be. For example, if it's going to be a Compton scatter, and then of course, the directionality and the energy, and just track that particle through the patient's CT. So now enough of all the theory. Let me go ahead and bring the software over here so we can give a quick look through the software. So this is the patient work list, and you can see the patient name, the status. Some of the plans have been approved, others are pending. I'll go ahead and throw in a plan to process while we're talking, so that you can see how quickly a plan processes. You can see that was simulating a DICOM export. The system shows that it's receiving the DICOM files, and it's beginning to process, and all that occurs automatically without any user interaction. So let me go ahead and open a plan to give that a few minutes. And so I'll open this prostate plan, perhaps not the best example for a Monte Carlo calc, but just to show you, these are the metrics. Of course, those are based on your ROIs. Next, we can go down, take a look at the DVH. You can turn on and off any of the structures that you do and don't want to see. Next, review the gamma analysis, a 97.8% pass rate, 2% 1 millimeter with a dose cutoff of 5%. The reference dose is selectable. Here it's the TPS, the global gamma analysis, and your voxel size. One can, of course, go into plan settings and change some parameters if you so prefer. Go in, perhaps if you would like to modify the uncertainty level. Extra fine means 0.5%, fines 1%, fast is 2%. Statistical uncertainty, you can modify that. There's ROI mapping and density overrides available. One can go in, modify the gamma analysis if you want to have, for example, IMSure 3D as the reference dose instead of the treatment planning system. Switch between global and local gamma, and of course modify your dose difference and distance to agreement. All those are easily accessible and can be modified for your particular plan. And so after the gamma analysis, the next item is your image slice viewer. You can review the treatment planning system dose, scroll through the slices, the IMSure 3D dose, or review the gamma comparison of the treatment planning system and IMSure 3D dose. In red, any items in red are where the treatment planning system is lower around gamma greater than or equal to 2. One is kind of this yellowish area. On the opposite spectra, the blue is where IMSure 3D is lower. And this is a hot-cold gamma. You can as well, if you prefer, look at the more traditional gamma, but the hot-cold gamma, of course, tells you your hot-cold areas in your plan. You can see the comparison is quite good. And then beyond your beam slice viewer, you can take snapshots. It'll be included in your report from your beam slice viewer, your image slice viewer, sorry. And then down here you can look at your beam information, your monitor units, beam dose differences, and some plan complexity metrics. You, of course, can approve the plan and then review the report as well as provide comments. So back at the patient work list, I meant to go back a little sooner. This calculation has probably been complete for a little while. I should have popped back here, partway through my explanation. But this has completed the computation, and you can go ahead and review, of course, the same items: metric, DVH, gamma analysis, image slice viewer, etc. So that ends my software demo. And just to summarize for a brief moment, I went over a high-level overview, provided some excerpts from AAPM TG 219 that ask you to consider in particular, the increased importance of calculation-based second check, the shared information that IROC phantom pass rate has a higher correlation to second check calc than IMRT measurement-based QA. I went through a little bit of algorithms, not history, not too much there, but why Monte Carlo? And the why Monte Carlo answers are: it's a highly accurate algorithm optimized for speed. The plan check independent secondary 3D dose calculation is very important as well. As important also is the water tank measurement data check as part of the beam modeling, and the treatment planning system commissioning check as well for those parameters such as your DLG. And the software is optimized for clinical workflow.